This brings us to the next section, which is the algorithmic section, and also the definition section, that we try to define what we really mean by consistency. I gave you a definition in the first section, and we'll see other variations to that definition also. We motivate that based on the implementation. Okay? So there are many dimensions of implementation. One of them is consistency. What happens if there are multiple people writing at the same time? We'll ignore that for now, and we'll go and focus on something I'm calling synchrony. Okay. So the definition so far is that what you want to do, what you've got is replicas of some object. So there's some object O1, it's got a replica in process P1 and process P2, and similarly you might have another object. And we'll just focus on a particular object. We'll assume the object is given. Okay, what we have to say can generalize to multiple objects. And we said, look, they're consistent if at all times they return the same value. And that same value could be a real value or a value that says it's undefined. So no, let me yes. So we'll go and say it's one of these two cases, and we'll go and vary these semantics later, but that's what we're going to define right now. So and we're going to take, I said there's only one writer, so there's only one person proposing values. That's a writer, and there can be multiple learners. And let's assume that there is no state kept anywhere else. So if we are using a server, it's only to relay, and so the algorithm can work with either a P2P architecture or a relaying server. Each algorithm we see can work both ways. Okay, and I'm going to basically assume there's no server. Okay, but we could do the same algorithm with servers. It's just a slight change where the message goes not directly from a proposer to a learner, but it goes through a relaying server. So let's look at the scenario. We've got one writer, multiple readers. Let's look at so that's the architecture. That's what I'm going to constrain myself to based on implementation. But let's go and look at the various situations in which we might need replication and see whether there's any examples here that would fit that architecture. In other words, which of the various cases I have here require only one writer and multiple readers. Okay. Put it another way, which of these scenarios are practical applications of the architecture we saw earlier? So let's go through scenarios. This will make us understand the scenarios better and the limitations of the architecture and the uses of that architecture. So let's make that the next question. Okay, realistic applications of single writer, multiple reader problem. So let's see first, multiple clients, UIs commit to a single server. Does that fit? David? Okay, that's true, that you can look at it that way. But I'm thinking of the Sakai quiz, that the client is the one that's making a change to the quiz and the server is the one storing the values. Where's the multiple readers? Yeah, but no, don't give up. So aren't the various writers writing different objects? So then it is what then? Oh, how many writers are there? Jason? And how many readers? Yeah. Yep, yep, yep. So there you go. It's even simpler than the architecture we had. Okay. Um, Nested transaction involving multiple logical servers. So you're trying to go and book a ticket on Travelocity. So you're one writer and how many readers? Sorry, yeah. So you have one. Uh, yeah, this is kind of tricky. So does it fit that? Let's not try to figure out what this is. Does it fit the single reader, single writer, multiple readers? Randy? Right, but given a seat on a plane, how many people might want to book it? Okay, but good, 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 good. I'm glad you're thinking. Okay. So, but there can be multiple people wanting to write to a seat, right? In the Sakai case, my quiz should not be written unless it's a collaborative quiz. There's no good reason for multiple people to write the same quiz. Okay. So if I could just reserve it, if there was, okay, if every plane would keep a seat for me, and the question is whether I'm taking it or not, that'd be great, right? Uh, so physical. So let's say that's okay. Physical replication with multiple changes. So again, by definition, doesn't work. Locks you need when you have multiple readers for physical So what about this? Physical mirroring. You Akamai and some servers changing, and there are a bunch of mirrors that are keeping the state constant. Jason? Good, good, good. Uh, primary master slave backup replication. What do you guys think? David? Good, good, very good. Okay. And master replication with disjoint writes and overlapping writes. David? But then there are two cases here where the masters are handling disjoint writes or this overlapping writes. This disjoint means that every master is responsible for some subset of the rights. So this master is responsible for Indian Facebook accounts, and this master is responsible for the Chinese, or I don't know if China has Facebook or not, but the US Facebook accounts. Yeah, okay. Yeah, yeah, okay. So let's go and record this now. So this fits. The quiz is being taken. We're talking about the quiz situation, and only one person should be able to write to a quiz. The server might store multiple quizzes, but for each object, the server is simply a reader of that quiz. There have been times when I've had to go to Sakai and say, please submit this person's quiz for them, and they've done it. So they do have the authority at times to do things to your quiz. I don't think they can change your answers. Okay. Here we talked about the airline and hotel case, and we said that this is probably multiple readers, multiple writers, because we're trying to reserve shared objects like seats and hotel rooms. So multiple writers could be wanting these resources. Okay, and this is by definition a multiple writer problem, and you don't need locks if you didn't have multiple writers. And physical mirroring, as Jason mentioned, if you have a server that's mirroring itself, master set is mirroring itself to a bunch of slaves, bunch of mirrors uh, who don't really write to the data, that just fits very nicely. And so let's go and see. So this fits. And I think I've got my arrow position a little wrong. This would fit if the slaves would not become masters later. Okay, but as David pointed out, these slaves are backup and they can become masters, in which case this wouldn't fit, but certainly this should fit. Okay, so I think I probably wanted this arrow to be. So before we go and do the full problem, let's do the Sakai problem, where there's only one reader and one writer. Okay, we'll call that the proposer being the writer and the learner being the reader. And this seems like a simple problem, but we'll see that if we want to do it correctly, achieving consensus here is actually impossible. Okay? So the way the proof goes, they actually use a more physical analogy. So they talk about two generals that are collaborating with each other to attack some enemy. So there's a leading general, and then there's a following general. I think the animation of the following general will arrive later, but the following general is somewhere here. And they both want to go and attack this enemy who's in between them. Okay, and the enemy is in a valley, and these two guys are on two different hills. Okay, so they have to decide at what time to go and attack. Okay? So the leading general proposes the time. It's going to be dawn or dusk or midday, whatever time, and they have to achieve consensus before they attack, because otherwise things can go wrong. So that's a problem. So the leading general must go and send a messenger, which in our computer system will involve a message. And the messenger must go through the enemy territory to reach the other general, collaborating general. And the messenger can make it or may be captured. So that's like the message not arriving or the message arriving at the other side. Okay, so let's say the general goes and says, okay, attack time is dawn, and the messenger reaches there. So the other general also says, okay, this is dawn. But the first general doesn't really know that the other general received the message, because this messenger might have been captured. So the following general sends another messenger saying, hey, I received your message, right? And now you see where the impossibility comes in. Now the second general doesn't know that the first general received the message. So we send another messenger, okay? And this can go on infinitely, and they would never really know whether consensus has been reached or not. Okay? So what do we do here? How do real systems solve this problem? I think I have that question, so let me go and see whether I go to that slide. And we somehow are able to send reliable messages, quote unquote reliable messages. So I guess there are two questions. Given my proof here, a very graphical proof, I mean, in a graphical way, it seems we can never achieve that particular kind of consistency. So if we don't achieve that, what do we achieve? Okay, when we use, and you guys who've done networking courses should know the answer better than the guys who have done operating systems. So so we can never achieve consensus. So how do we transmit messages reliably is the question. Okay, so this whole idea of sending acts to acts to acts to acts just goes on infinitely. And I'll let the basic idea is that you send a message. If you don't get an act back within a certain time, you send another message. Okay, so that's the idea of sending duplicate messages. And we'll go and say that we want to send a buffer, and it's going to either return true or false, saying if we were able to send it. We will receive in a buffer, it's going to return true or false whether it received it. And again, without looking at TCP/IP in depth or at all, it's been a long, it's been a long time since I've seen the algorithm. Unlike you guys, actually, I haven't taken either a distributed systems course or a networking course. In my time, these courses weren't really taught. So so we go and wait, and the amount we wait may depend on which number the message is in the duplicate sequence. Okay, so we go and say, okay, we'll go and if the ACK is not received within a certain timeout, that depends on what the sequence number is in the duplicate sequence. We'll go and retransmit the duplicate message. Okay, and it's successful if ACK received original or retransmitted message, and we don't send a duplicate message if we have gone and sent a certain number of duplicate messages. Okay, so we wait for a certain number of we stop here sending, just as David said, that after we've gone and David said it was 3, so we go and wait for 3 messages. We send at most 3 messages, and after 3 messages we give up. Okay, and here every time we receive a message, we send an ACK in response to each received message. And if we don't receive a retransmission after a certain time, then we say, okay, the sending party has failed, so let's just give up. So that's, I believe, how TCP works. But that's certainly an algorithm to go and use timeouts. Okay, so this is not perfect guarantee, right? This is you're assuming certain characteristics, and you might give up earlier than you needed to give up, and you might give up and you needn't have given up, which is another way of saying you gave up earlier than you should have given up. Okay, so that's a practical implementation. And what we're going to do is we're going to assume that, in our discussion of algorithms, we're going to assume that processes don't die, and messages do get sent always. Okay, with enough, the network doesn't get partitioned, processes don't die, and our timeouts are well designed. So when we send a message, the messages will receive be received at the other party, and they'll be received in order. Okay, that's what TCP/IP guarantees. So we'll make that assumption for the rest of the course, and we'll see what else we have to build on top of this form of consistency to get replica consistency. Okay. So again, we've got this problem here. We can go from this particular situation to multiple readers. And what we'll do is we'll go and look at the algorithms. This is a distributed algorithm. So there's the algorithm being executed by the proposer and by the learner. Okay. And the proposer goes and we'll go and model the proposing as follows. That the proposer sends values to learners, and that learner may be the proposer itself. Okay, if the learner is the proposer itself, it makes a local send. Otherwise, it makes a remote send. Okay, so the state of the shared object changes when a learn notification arrives. Okay, so the proposer sends a value, and we'll assume that there's always a proposal number and a value. Okay, the proposal number is not going to be relevant in many of the algorithms, but for now, let's assume that there's it's always sent. And so the algorithm at the proposer end is very simple. You just send the value. You somehow generate the proposal number, and you know what value it is because some client thread when it told you this is the value they want for the object, and you go and say, okay, this is the proposal number for the changes to this object, and here's the value. And the learner receives the proposal with proposal number and value from sender, and whenever it does so, it goes and changes the state. It learns the value. Okay, that's my simple algorithm, and that's pretty much what you guys have implemented in your assignments 3 and 4, except you went through a server. But in terms of consistency, that's what you're doing. And you may or may not have thought about problems of consistency. But let's go and evaluate this algorithm and see whether it really meets the requirement I laid out. And if it doesn't, we'll go and change the requirement. So the requirement was that at all times, PI, the replicas of the same value, or the values are undefined. Okay, and we'll go and actually the way I presented it here, this is something we'll never implement. But we will implement something that's a small change to this particular requirement. Okay? So my claim is that the algorithm we have does not meet this requirement. So let's try to understand, and this shouldn't be too complicated. Let's try to understand where our previous algorithms is failing, assuming we're using TCP/IP, assuming messages get an order, assuming messages do arrive at the other party, where are we not meeting this requirement? Okay, so the answer is no, and why not? So messages can be received at different times at different sites. So we do not meet this requirement, even with a single writer. And we never invalidated the value. So we had the invalid idea of an undefined value to account for the fact that there is propagation delay, and we never did invalidate. So that's the reason we don't quite meet this requirement. Okay? So, but this is what you guys do. This is what many algorithms do. So let's give it a name. I mean, it's not that we are totally irresponsible, that we're doing exactly what we want to with no guarantees. We are giving some guarantee, but the guarantee is not as strong as what I've got here. So let's try to think about formalizing the guarantee that we are giving. I mean, we are, whenever the proposer does go and make a change, the proposer does go and send the message to everybody else. We are guaranteeing that the message arrives at the other end. So what does that amount to in terms of the state of the object? Okay, so how do those actions, what do they have to say about the guarantees of consistency? So let's try to formalize what we are doing. We can't quite formalize it using this definition, so maybe we can change the definition and use that to formalize. Oh, I guess okay. So this is, before we go there, I'm just going and showing you exactly what David mentioned. So you propose the value here. You learn this value immediately, maybe a little later, because your learning thread may be separate from the proposing thread, which is how my implementations have done. And you change the value. This is, let's say you're trying to agree on the meaning of life, and you say, okay, it's 42. Everybody else thinks it's 0. So they're already not consistent at every state. And now this one becomes, I guess I've got the order wrong here. But they become basically 42 in different orders. My animations are not quite right. Okay. So, so the situation we talked about, is graphically illustrated here. So now we get the question, what requirement do we meet? And let's try to go and answer that question. Okay. So how can we weaken the requirement so that we know we give some guarantees, but don't give the guarantee that we've written down so far? So we're going to go and define. So here's our definition here. We can assume pure replication, synchronous replication, where we say at all times t, for every pair of processes ij belonging to set some d of processes, state it is equal to state jt. Okay, so we look at time also now. So we can say that pure synchronous is this. We'll try to go and achieve this using some realistic, unrealistic assumptions. That's pure synchronous. And what David said is called asynchronous or eventual consistency. That if we look at the commit time of some proposal P and the submit time, then for each process belonging to the set of processes, the commit time of that value minus the submit time is finite. Okay, it's going to be, eventually we will get that value. Okay, and there's an issue whether the set D of processes we're considering can change dynamically or not, and we'll just make our life easy by saying it's a static set. Okay, so we have to go and use time in our consistency definition and decide whether we are going to achieve consistency at all times, or we're going to have eventual consistency, that the value we've made, change we've made, finally gets reflected, eventually gets reflected on the other side. Okay, so we'll call this asynchronous or eventual consistency. And if you go and Google eventual consistency, I'm sure you'll get a lot of hits. Okay, it's a very old concept, and many implementations provide essentially eventual consistency. You think of Facebook. You make a post. You don't know when somebody else will receive a post, but eventually they will receive a post. Okay, and before Facebook, my generation used to have something called net news, and net news was basically the same idea that you would post a message and it would arrive at reach other processes. And people decided that, look, trying to implement a very strict algorithm was too expensive. So that was actually a multiple writers, multiple readers situation. And they had even weaker consistency with it. When you have multiple writers, the set of messages that you get is finally eventually consistent, but the sequence may not be. Okay, because my message may come after your message to one reader and before to another reader. Okay, so we just, depending on what our application is, if it's a forum, who cares in what order people will figure it out, if there's any dependency. So we've got eventual consistency and pure synchronous consistency. And what I defined earlier is neither here nor here, and we'll go and try to define that as some intermediate point between these 2 points. Okay, right now we know how to do this. Let's go and try to do this, and if we give up, we'll try to go and do something in between. Okay, and we will give up eventually. Okay. But let's try to go and achieve this first. It seems impossible, but with some assumptions, this may be possible. So let's go and see how we can do synchronous replication. Okay. So can we implement synchronous assumptions, making some assumptions? Okay. And the assumptions can be of various kinds. You guys are free to choose the assumption. This is a discussion I expect to be long if we go through all the possibilities that I have in mind. So we can fix the maximum time to receive a message. Assume that we know there is a maximum time t by which a message will arrive at the other end. Okay. And it seems from the discussion of TCP/IP that I heard from you guys and the one I gave, such a time does exist. We can assume one or more of these assumptions. We can assume that there's no variance in time to receive messages, that all messages arrive with the same delay at all sites. Okay, this is a very simplifying assumption. And we can also go and assume that the clocks on different computers synchronize. Now that's you might think, of course, that's easy, but that it is not. Clocks drift, and if you try to go and synchronize through a server, then again there are times when you'll be not synchronized. So this is an extremely difficult problem. Okay, and the fact that clocks are not on different computers, not synchronized, has been used to develop a variety of algorithms. But let's go and assume for now that they are. Okay, so we can assume any subset of these assumptions or more. But let's go and see with these assumptions, can we do synchronous replication or not? And the answer is yes, we can do. Also, these assumptions are not that realistic, but when we go to the intermediate algorithm, we'll see that it will be a small change to the one we come up with for synchronous algorithm. Okay, so we've seen the algorithm here, we'll see the algorithm here, and then the intermediate algorithm we'll develop will be in between these 2 points. We'll use ideas from both of them. Okay, so let's again have some discussion. So let's assume that the variance in time to receive a message is 0, and there's a constant message transmission time. In this case, the proposer just sends the proposal number and value to all learners, and remote learn just goes and receives proposal with proposal number and value from sender and learns the value. It doesn't do any waiting. And the local learn receive proposal with proposal number and value from local sender, delay for constant message time, transmission time, and learn value. Okay, this is assuming that the same thread is doing both tasks, sending and learning. And this is an important issue. Like I said, when you have multiple threads, who knows when this particular thread will execute it? So in that case, this thread would have to know the sending time also. Okay, but I'm assuming the same thread does the work. And then we said that the algorithm that Jason and Chris and David and everybody got together said that, look, let's go and assume that the sending time is we have a maximum message transmission time, and somehow the sending time was important to the receiver. That must mean that there's 0 variance in global clocks. Okay, so we assume there's no variance in global clocks, and what we will do is send with proposal sending time, proposal number, and value to all learners, and we'll receive the proposal. We delay until current time is sending time plus maximum message transmission time. So we'll all delay changing the value. We won't go and change the value immediately, and then we'll learn the value. And you must send an extra bit of information or extra bits of information sending time. And you know there's sort of the space-time trade-off. So there's another algorithm I'll just give you next that reduces the space but increases the time. So we make the same assumptions. And what we do is we fix the times at which we send information. Okay, so the word synchronous makes much more sense here. Imagine there's a clock ticking, and only when the clock ticks will we send the message. So if we have a message before a clock tick, we wait till the next clock tick. Okay, so the clock ticks at time 0, the clock ticks at time t, where t is the maximum transmission time, and so forth. And suppose we want to make a proposal at this point. We wait till the next clock tick. That's when we send the message, and it gets received at different times. But the learning always happens at the clock tick after the one in which you receive the message. Okay, so now you have an extra time that if the message arrives immediately at all sites, then so basically the problem is that you waited this much time before you send the message. So this is kind of a variation of what Chris was trying to say earlier, that somehow it's programmed. So no, it's not programmed when the person will send, but it's programmed at what clock ticks it will send. What are the discrete intervals it will send. So there's an extra delay here before sending a message. This is an extra delay, sorry, here, sending the message. Okay, we waited this much time. So this is what I think, I hope I got this right. I just wrote it this morning. We delay until current time div max time is equal to 0. Well, this should have been mod, right? So this should have been mod. And so we assume that is exactly divisible by that. And send proposal with proposal number and value to all learners. And local learn, receive proposal. Again, this should be mod. Delay until the current time is exactly divisible by max time. Okay. And learn value. So worst case transmission time can be large, and global clock is unreasonable. So we'd like a better algorithm than this. Okay, but we're getting there. So we want to give up on synchronous and do better than asynchronous. And this is where we will go and change our algorithm. So we'll have this invalidate protocol. And it's a slightly more complicated than the one I gave you earlier. And what I'm saying here is that because that assumed that at all times they are the same value, either they're all the correct value or they're all invalid. No. If they are not invalid, then the value is equal to all other values that are also not invalid. Okay, but if they are invalid, then other values can be valid. Okay, so if you ask somebody a question and you say, look, I don't know the answer. Okay, but the correct answer may exist as some other mirror, but I don't know the answer. I won't give you the wrong answer. But if you give the right answer, it is if you give an answer, it is the right answer. Okay, that's what this is trying to say here. Okay, so if state ij is not equal to null, which is invalid, then state jt is equal to null, or state jt is equal to state it at all times. Okay, that's what this is trying to say, what I said earlier. So now we go in. So we've got this new form of consistency, and what we'd like to do is now change our let's go and I said that this new form of consistency will allow us to go and get rid of both of these assumptions. But let's do that also incrementally. Let's try to get rid of this assumption first, and then get rid of this assumption. Okay. So this says student discussion. I hope I have a student discussion slide after this. Otherwise, I'll just give you the answer. So let's go and see how we can go and do this algorithm without assuming variance in global clocks. But we can assume a maximum message transmission time. Okay. And so what we'll have is the answer that you might be thinking of is two phases where you get responses from other sites, but we'll assume there's no responses. Okay, you just send the information, and at some time you go and change the value, and in between you go and invalidate yourself. So that's a protocol. We can assume there's a known maximum message transmission time, but we don't have to go and send our time. We don't send our times because there's no global clock, so we don't do that, and somehow we still achieve that weaker form of consistency. So think about that. So this particular thread proposes, learns it immediately, says pending. After time t, it will go and say it'll go and make it commit to the value, and everybody will do that. Okay, and they go and correct the value at different times, but when the last person corrects, um, so whenever they do correct, it is equal to a value that's been corrected earlier, and so we achieve the goal that we had. Okay, we never have two committed values being different. Okay. So we wait. Okay, so we can achieve consensus here first, then consensus here, then consensus here, and so forth. Okay. So in worst case, time t is large. So again, we have waited too long a time. I mean, we waited longer than we should have had to. That's because we were trying to do it all in one phase. So let's try to go and make it multi. So here's a trade-off. This algorithm does have safety. Okay, we do make sure that we don't agree on different values. Okay, either we say we don't know, or we say when we give an answer, it's correct. Okay, so it's safe, but the progress or liveness or the delay is not so good. Okay, there was a long period during which there was a period when nobody had the correct answer, and there was a long period, there, a large amount of time elapsed before everybody had the right answer. So we'd like to get the progress and liveness quicker. Okay, we'd like them to go from the invalid state to the valid state earlier. Okay, and the question is, how can we do that? And now we will allow for more number. Again, this is sort of a I don't know if it's space time, but we are going to send more messages. So in that sense, it's space and time um, to achieve consistency. Okay, so let's try to think of that. So let's go and have two phases, and let's assume that we have acts. So we already have acts to get a reliable communication, right? Those are the TCP/IP acts. We're going to add additional acts here. These are application level acts to achieve this form of consistency, where we don't have to go assume a certain maximum message transmission time, and we don't have to go and delay needlessly our transition from the pending state to the committed state. So think about that. It's not too hard. So this is what's happening. We have proposers and we have learners. And to make this very general, we'll have a bunch of acceptors. Acceptors are the ones that will go and send acknowledgements back to proposals. Okay, so that's the red line here. The purple line send the initial is the initial phase initiation, and the red lines are the initial phase termination. And after the red messages arrive, at that point the proposer goes and sends the message to the learners. Yeah, and as Andrew mentioned, the proposer goes and sends the message to all the acceptors. The acceptors go and send ACK back. Once the proposer goes and receives all the ACKs, it goes into the second phase where it goes and tells people to go and validate the value. Okay. In general, the set of proposers, acceptors, and learners are the same, but a lot of algorithms separate them. So I'm just using these different terms. So assuming they're the same, the proposer sends the value to every process. The process, when it receives this particular purple message, invalidates the value and sends an ACK back. And so the value is invalid during this time period. between when the purple message was received and the red message was sent back. And when the green messages arrive, at that point, the second transition, okay, back to the committed value. Okay, so we're going to call this a synchronous algorithm. The first algorithm we saw when we had clock ticks or sending time sent, and at all times the value was same, we'll call that the pure synchronous. Yeah, this is sort of the realistic synchronous algorithm. Okay. And the eventual consistency algorithm will be the asynchronous algorithm. So here's the proposed value. It gets immediately accepted by the local site, so it becomes pending. It goes to another site, that becomes pending, that sends an ACK back. It reaches another site, that becomes pending, sends an ACK back, and this continues. And at this point, all ACKs have been received, so we know all values are pending. So we can go and now send the learn message, which can arrive at different times, at different sites, and we have consensus. Okay. So our algorithm is we send accept request to all acceptors instead of notification to all learners. Acceptors will usually include self, like I said. And when would acceptors not be equal to learners? So imagine that learners can be, we have slaves versus mirrors. So the slaves are the ones that you want to ensure have truly the correct values, and mirrors, can give the wrong answer at times. So we can assume that we are only concerned about the algorithm working correctly with the slaves. So we have now three algorithms, okay, and the accept algorithm is you invalidate state, send response to sender, and we have also an accepted algorithm. So now we have the accept response being received at the proposing site. So if not sufficient notification, record notification return. And if you send learn notifications, have sufficient messages. Okay. So with this accept phase, we can do a greater variety of problems. Okay, we don't have to we don't not only provide a different form of synchrony, but we can also provide different semantics. Okay, so far our we had a following general and leading general. What about a leading general and a thinking general? Okay, so the leading general says attack at dawn, and the thinking generals can. There's still one writer, but the thinking general can say, "Nah, I don't think it's a good time." Okay, since we are sending acts back, we can send back an act saying I agree or I don't agree. So with two phases, I can do a greater variety of problems. Okay, so it says attack at dawn, says no. So receiving general can reject, unable to process request. Okay. And this problem is compounded when you have n rejecting generals. And the general could reject, or the general could veto, or general could veto. So we can accommodate both situations with this two-phase algorithm. Okay. So we can take majority or allow veto power or do something else. So let's think of how we might change our algorithm to and it's a small change, but let's go and think about that. How do we change the algorithm to support rejection? Let's assume for now that a rejection is a veto. So we can also send a negative learn. So we propose a value, and let's say the value arrives, is accepted, it becomes pending. So as Andrew mentioned, now we go and send back not only the fact that we received the message, but whether we agree or do not agree with the proposal. So here we are saying we are the proposer. So hopefully we'll say yes. It becomes pending here. Let's say they say no. Um, Actually, the algorithm I've got here is looking at majority, I think. So it sends a message. So this no doesn't result in any learn notification being sent. So it becomes pending at this site. It sends no to. At this point, majority have decided no. So it goes and sends a message saying, hey, all your pending values, undo and go back to the previous value. And by the way, the previous value was, well, they can store the previous value. Okay. So the new value was supposed to be 42. It says, by the way, for the 40, it doesn't have to resend 42 again, but in my pictures here, it does. And sends no, and so they go and undo their values. Okay. Okay. So the loan notification is sent to these two sites, and we get consensus eventually. And the interesting thing is that these two no's were sent before the proposer sent the message to this last site. So the last site, never knew that this value was even proposed, and it all works out because the way Andrew described the algorithm, that the moment the proposer learns that the value is rejected, it goes and sends a notification, and so it works out, okay, about the learn notification. And it can send the learn notification, not only negative learn notification, but it can also send a positive learn notification before it has received all the responses, because we are actually looking at majority here. Okay, so uh, it can send this value, and these things can also arrive in the wrong order, so it'll all work out. Okay, let's look at the situation here. The proposer proposes a value. It's accepted locally, becomes pending. Yes. Um, it sends the value to another site too. That also says yes. Sends it to another site. Sends yes. And it goes and sends a learn notification to everybody. Okay. Now, okay. So we have a problem here, right? That it hasn't sent the value. So the way I describe the algorithm seems to have a problem. Okay, I seem to indicate that there's no problem if we go and send the learn notifications early. But see what's happened? Uh, these values are all 42, this is 0, and none of them is pending. Okay, so we can send a negative notification early, but we shouldn't be sending the positive notification early. Okay, or if we send the positive notification early, then we should make sure that all processes receive that notification. And so what happens, let me see this slide here. So this seems to be not synchronous replication. The consensus values are different. Okay, so we should really wait till we get all acts before we go and send the learn notification. Okay, so that's what I'm trying to say here. That we can send the negative value early, but we shouldn't send the positive value early. Early meaning that we haven't waited for an act from all sides. Okay. Um, so so we don't we I think it's time. Um, I'll continue this. I think I have 10 more slides that I can probably finish, and those of you who have to leave can leave. But I would like to finish the section. Okay. And I think I have more questions too. So so we'll continue on. So this is really not what we want based on the algorithm we had. But I'm going to argue this is not a bad thing to do. In fact, this is exactly what happens in many servers. Facebook does exactly this. It doesn't wait for acts from all the sites. It waits for acts from majority sites before it even goes and agrees on the value. So it can be possible that some sites have a value that is inconsistent with other sites. Okay. And this is consistent with what I'm saying earlier, that some of these may be slaves and some of these may be uh, mirrors. So this is another way of saying that we only wait for that the waiters and the acceptors and learners are different sets. Okay? That the accepting set is smaller than the learning set. So I started off by saying the accepting set and the learning set can be different. I gave you an algorithm. Then I went and assumed that they were the same set, and I described the algorithm, and it didn't seem to work out well. But it does work out correctly if I assume that only a subset of the sites are accepting sites. So, and you can also say that you can describe this algorithm, the algorithm I've described as in two different ways. We can always say that we don't care about the site. Okay? So we only care about these sites because these are the slaves. Or we can say that as long as there is some set of um, uh, acceptors as long as the majority of acceptors have agreed, we go and update the value. So we can model it two different ways. And even the second way, where I'm saying we only wait for the majority of acceptors uh, to accept the value, um, is reasonable in practice. Even if all of these guys were slaves, we might say that, look, we are just waiting for a subset of the slaves to go and accept, and some slaves may be inconsistent, and that's okay because this subset can then go and have a backup of a correct value. Okay, so there is something called two slave. I googled last time I presented this algorithm, and typically, as long as one slave has got your value, you go and accept it. You send the learn notification because you know that that slave has got your backup, so it works out. Okay, so so we don't wait for this notification. So we've got now we had these three algorithms, and we go and develop another algorithm, which is we know that for some set uh, E, which is a subset of D, this particular guarantee holds. Okay, so it's not for all of them, but for some subset, and that subset could be a dynamic subset or a fixed subset. This particular guarantee holds. Okay, that's the algorithm that I just showed you, which is not quite the algorithm that Andrew had described, where you send the negative acknowledgement perhaps early, but not the positive one. Here you can send the positive one early too, as long as some dynamic or static subset of processes have your state, okay, because you can back up the information from them. Okay, so E is a subset of D, okay, and E is not equal to the empty set. So we have the accept algorithm. Let's go and describe this. Let's describe both forms of the algorithm here. We invalidated, so we have these new steps, accept and response to accept. So we invalidate state, we calculate verdict, say are you going to agree or not agree, send verdict to sender, accepted, if not sufficient notification, record notification return, otherwise we send the learn notifications, and if proposal is not pending, we return, and if proposal member be vetoed, reject proposal, maybe send learn notification. So there's some debate in the literature regarding whether you should send negative learn notifications or not. As it turns out, many algorithms work quite well if you don't send negative acknowledgements, okay, negative notifications. But we'll assume that they are sent. I just wanted to point this out. Okay. And if the proposal group is rejected, so this is vetoing. And if a group rejected it, that means the majority rejected it, then either don't send a message or send learn notifications. Okay, so either you can it's like you only send good news, you don't send negative news. So if you don't go and send the negative news, maybe after some time out those guys go and invalidate the state, Okay, so there's many possibilities there. We won't go into them. Okay, so that's the algorithm at the algorithm to process the accepted notifications. And here's some practical applications where this whole idea of rejection can make sense. So what I used to do when I would teach at an earlier hour is that I would make my slides at home, and about half an hour before class or an hour before class, I would go and shut my laptop and go to the office and resume work from there, using Google Drive to go and make my files consistent. Okay? And there are two dangers here. One is I shut my laptop lid before it has synced, so I reach my office and don't have the files, or I give it enough time, but Google decides it's unsyncable file. Okay, and you see here, I have all these files that Google thinks is unsyncable. Okay, so it rejected my replication request essentially. So this is where it would be useful to have the notion of this form of consistency. So I know that this is invalid, so I can try again. I can email it to myself. That's what I typically ended up doing. I can create a copy of the file, and then Google would succeed. Okay. So reason for not accepting. So we want to know if file has reached server before shutting down laptop. Um, so so there are many reasons it could reject because there are conflicts, but typically Google and Dropbox just create duplicate files. But maybe it's not savable. They can, it doesn't have space. It found the file to be corrupted. So many reasons. Okay. So so you see here that there are reasons that Google has given me in the past for rejecting my changes. And I want to go and motivate a design pattern too. You guys will be implementing this, and we've talked about the observer pattern. There's another pattern called the VETOER. So that's basically the idea that when you make a change, you broadcast it to all learners. In Java and in general in the literature, there's also the VETOER design pattern, and which is a pattern under which you have not only a listener but also a vetoer attached to some changer, and the vetoer can go and basically after you make the proposal and before you go and change your own state, you wait for the vetoer to go and give a response. Okay, so that's actually a design pattern that is applicable even in the single process case, and essentially we've shown the implementation in the multi-process case with two-phase commit. Okay, and to make this all a little bit more real, I've actually implemented this algorithm and traced it. So we see here the algorithm working. So let's assume that this is a following acceptor who always agrees to everything that is sent, every accept request. So I think I have some arrows. Yeah. So it goes and sends a notification saying, "Yep, I agree." Okay, but it gets a denial. Okay, so while it goes and agrees to the value, the total result is denial. And that's because there's another acceptor who vetoes. Okay, so here we go. This particular acceptor vetoed, and that's why the service denial message was received. Okay, and um, let's look a little bit at our general algorithm and the data structure. Originally, I'd planned to show you the algorithm in more detail than what I've shown here, shown so far. But let's try to understand the data structure that might be involved here in doing the accept. Okay, so let's look at this particular thing here. Let's look at this data structure here. So this is at the proposing end. It gets a proposal accept response received, and it's trying to figure out whether sufficient number of agreements have been achieved or not. Okay, when they are, it sends a learn notification, and when they haven't been, it goes and does nothing. So to determine if sufficient agreements have been received, it needs to keep a data structure. And this line here shows you that there are 4 components to the data structure. Okay, so let's try to imagine what these 4 components might be, or in other words, what kind of what kind of information does the proposer have to keep to determine if sufficient agreements has been reached. And if you can't think of all 4 components, just think of a subset of the components. So here's the data structure, Y4 tuple. Or another way to say that is what should really be kept. So last time we were looking at synchronous consensus, and we saw that there was pure synchronous, asynchronous, and synchronous. And in synchronous, we had not only the value of a shared object, but also the state of the object, whether we have achieved consensus or is the value pending. And we saw that it was a 2-phase algorithm. A new value is proposed, a new value is learned as an asynchronous, but also when a new value is proposed, it doesn't simply get learned. It has to get accepted by a bunch of acceptors, and depending on their response, the value may or may not be learned. Okay, so the really tricky issue there was what to do with the various responses to the accept request. Okay, and we had 2 alternatives. We could allow vetoing, where a process could say, look, I reject this value. So if you're doing a Travelocity reservation and you're proposing both a hotel and an airline and maybe even a car rental, then the airline can veto, and your whole action, the set of actions which is called transaction gets rejected. Okay, or if you're trying to save the value to a bunch of slaves, and one of them is having trouble saving the value, maybe if the majority of the slaves go and save it, then you're happy. Okay? So it could be we could support a veto notion, or we could support a majority agreement, or we could require a unanimous agreement that everybody has to agree, otherwise we will not change the value from one committed value to another. Okay, so you have 2 alternatives there. And when an accept notification comes in, we might just record notification and take no action. Okay, so if we are in the veto mode, if there's been no rejection so far, we just do nothing. We are not ready to go and tell everybody to change their value. And if we have received a rejection, but there is not been a group rejection, we again record the value and wait till we have enough people to go and give the consensus value. Okay? And there are 2 cases here. So if bad news comes in, okay, say a rejection or a veto or a group rejection, we can send the learn notification. Okay, so here we send the learn notification when we got a rejection here, and here also we sent a learn notification when we determined rejection. Okay, so bad news can go quickly. The good news may or may not go when it is determined. Okay, so if we are doing synchronous, we want everybody to put their value to pending before we send any good news. Okay, because we don't want 2 sets of committed values. One set of replicas having one committed value, another set of replicas having another committed value. Okay, so we wait for everybody to be pending, and then we go and send the new committed value. Okay? In semi-synchronous, the good news can go early too. So the moment we notice that we realize that a majority wants agreement, we go and send the consensus agreed on value. So now we can indeed have 2 sets of replicas with different values, but we don't care. Ultimately, we will achieve consistency, and we know that the proposed value is committed at least one other computer. from the one that proposed it. Okay, so there is the special case of true synchronous, where a master proposes a value and it gets back a message saying from at least one slave saying, "Hey, I agree and I've received the value." And at this point, the master says, "I'm going to go forward because I know if I fail, this particular slave will have the value for sure." And other slaves, if they're alive, they will get the value eventually. Okay? So that's semi-synchronous. So there's synchronous and semi-synchronous. And in semi-synchronous, what can happen is that we have sent the learn notifications. We've determined the good news, the correct news. And after the news has been determined, we get a accept notification. Okay? And even actually in synchronous, that could happen because the bad news may have gone earlier, and um, and then we may get more notifications which we don't care about. So at this point, we just return without changing our state. So we have to be ready to get late messages that arrive after the decision has been made. And in semi-synchronous, this decision could be positive, and yet we might receive messages after that. In synchronous, if the decision is positive, then we will not get um, late messages. So that's the difference. Okay? So uh, accept response may arrive late in semi-synchronous, even when there is agreement. Okay? That's what I should be saying here. Accept response can always arrive late uh, uh, in both synchronous and semi-synchronous if it has been if the value had been rejected. Okay. So this is something I've actually implemented. So this particular enum here gives you the alternatives. We can be asynchronous, we can be completely synchronous, and then we can be majority synchronous, where we send the good news early as soon as majority agrees, or we can be too synchronous, where as soon as one other process tells us they've received the value, we go in and agrees to the value, we go in, send the good news. And there's another issue that arises, which I didn't want to dwell on too much, but since I did implement it and some of my traces show that, let me talk about that. So what happens if there's failure? Okay. So far we've been ignoring failures, but in general, we can have the set of members vary. Okay, so we can have the current members be different from the initial members, different from the maximum members that we ever had. Okay, so processes might come, fail, and go. So this set can change dynamically. And we're going to assume mainly that we have a static set of members, but the data structure I talked about last time actually accommodated dynamic set of. So synchrony determines there are two issues here. Majorities are used in two different ways. So one to determine when we send a positive value. Okay, that's what synchrony determines. Majority is also used to decide what the consensus value is. Is it based on a group consensus or vetoing or unanimity? Okay, so that's an orthogonal issue which is not being addressed by synchrony itself. Okay, so that's important. And they are related. If you're supporting semi-synchronous, then you cannot be supporting veto because you're not waiting for everybody to tell everybody's accept notifications. As soon as you get a majority of accept yeses, you send the good news. Okay, so you send the accept the proposed value. So in semi-synchronous, we have to assume there is it's not veto, whereas in synchronous it could be veto or group consensus. So that's an important point. And we can now understand the data structure uh, uh, we talked about. So this shows us what kind of information we need in the proposer. to determine if sufficient agreements has been received or not, and to determine when to send notifications and learn notifications and what the learn notification should be. So I said it's a 4 tuple. Actually, it's a 5 tuple. So there's 1, 2, 3, 4, and there's a fifth piece of information too after the question mark. Okay, so this is the first item is the number of accepts. We have agreements we've got. This is the number of notifications we received, and these two values determine the current members versus the total members. And since we are not really dealing into this issue, we see it's always the same. These are always the same values. So we're talking of 4 processes here. Okay, and right now this last value says how many agreements do we need? Do we need before we go and give our positive news? Okay, so this says that how many notifications do we need before we send positive notification, and this says we need to receive notification of everybody before we go and actually give a learn notification, send a learn notification. So let's see what happens here. I get 1 accept notification, and that is the only notification I've received so far. I get 2 notifications, both accepts. 3 notifications, all 3 accepts. 4 notifications, all 4 accepts. We have got 4 notifications, so time to go and send our positive news. Okay, and we send that success. Okay, okay, restart here. Okay, so this is majority. Okay, I was looking at the wrong piece of information. This is majority, 1 acceptance, 1 agreement, 2 acceptances, 2 agreements, 3 acceptances, 3 agreements, and I get a service denial, but I am doing majority. Okay, so we get proposal consensus, and I send back the value 42 with a yes. Okay, this service denial happens to have to do with another proposal, and I'll talk about that later. I didn't see this as 29. I was showing you what can go wrong when you have 2 people proposing, and that causes inconsistency, which I won't get into because we'll just go and see how that inconsistency can be solved. So indeed, we are doing majority consensus. I forgot my slide, and we waited till all 4 messages arrived till we sent the good news, because we were required to go and wait for 4 of them. Okay, that's what the situation is. Okay, so we waited for 4 notifications. Now let's look at semi-synchronous. Okay, so we are going to wait for 2 majority of 2. So and we're going to send it early if that majority arrives early. So we get 1 acceptance. We do 1-1. So we are both the proposer and the acceptor. So and we get here a service denial here. Okay, so we have 1-2, and like I said, we are both the acceptor and the proposer. So we get our own accept request. We sent our own notification saying we agree. We as proposer received that response, and now we've got 2 agreements out of and out of 3 notifications, and we declare success. Okay, and we go and send this value to everybody else, and we receive that notification ourselves, and we change our state saying this it's proposal consensus. Okay, successful, and we finish waiting, and we then get another response later to this 29 value, not 42 that I was talking about earlier. And that's okay. This is just a late message, and it didn't change our mind. And even if it was a failure, it wouldn't change our mind. So this shows you that we can indeed receive things. We can send the good news early. Okay, so this shows you in the traces. So now I'm talking about the fact that there's this 29 value, there's this 42 value also, and they're both competing. And I didn't talk about the 42 value. but things would get messed up, as you can imagine, if there are two proposers sending values at the same time. Okay. So in these traces, a concurrent proposal of 42 is made. We are ignoring them as we're currently focusing on one writer, multiple reader case. Multiple writer